Hi everyone, my name is Alexandra Pierce and I'm in Physics 2211 at Georgia Tech. This is Lab 4 titled Oscillations. The purpose of this lab was to observe and measure the motion of a mass swinging in an arc while oscillating on a spring. Then this motion was analyzed using Tracker. A computational model was used to predict the object's motion and plot the predicted energy changes. The goal was to determine if the model system satisfied the energy principle. The results show that the total energy of the system remained equal to zero, meaning the energy principle was satisfied. The two fundamental principles used in this lab are Newton's second law and the energy principle. Newton's second law states that the net force is equal to the change in momentum over change in time. Net force is also equal to the sum of forces acting on the system. There are two forces acting on the mass, a spring force and a gravitational force. The net force can be used to update the position and velocity of the mass. The energy principle states that the energy of a system is equal to the work done by the surroundings plus heat. In this experiment, the system includes the mass, the spring, and the earth. This system should be a closed system, so it is assumed that there are no outside forces acting. This means that the total change in energy of the system should be equal to zero. In order to satisfy the energy principle, there should be no change in total energy of the model system. In this experiment, the change in total energy is equal to the sum of kinetic energy, spring potential energy, and gravitational potential energy. I include some formulas that will be utilized in both the observed and computational models. Let's start with the observed model. Here's my video analysis of the mass's motion and tracker. As you can see, there is oscillation in both the x and y direction. The mass of the object is equal to 0.402 kilograms, and its initial velocity is equal to 0 because it started from rest. Some calculations using the observed data were required to get the initial conditions needed for the computational model. First, I had to calculate the period of oscillation for the y direction. I did so by dividing the amount of time it took to complete 3 total oscillations by 3, which came out to be 1.524 seconds. This value was then used to calculate the spring stiffness, K, which ended up being 6.83 newtons per meter. Using this value in the initial stretch of the spring, I was able to determine the relaxed length of the spring, L naught, which was equal to 0.123 meters. Now it's time to create the computational model. Here's the code I created for the computational model. First, I defined the initial conditions that were measured and calculated using the observed data. Then I calculated the stretch of the spring by subtracting the relaxed length of the spring from the magnitude of the spring's current length. I then used the equations for kinetic energy, spring potential energy, and gravitational potential energy to find the energies of the system and add those together to compute the initial energy of the system. Then I used the equations for the gravitational force and spring force to compute the net force of the mass at each time step. This value was then used to update the velocity and thus the position. Lastly, the final energy of the system was computed at each time step, and the change of energy was calculated by subtracting the initial total energy from the final total energy. Here's what the code looks like when it runs. When looking at the change in energy graph, you can see the changes in gravitational potential energy and spring potential energy oscillate with the same period as the position of mass changes. When the spring potential energy increases, gravitational potential energy decreases, and vice versa. The change in kinetic energy are both positive and negative because the mass gains and loses kinetic energy, with the kinetic energy change being equal but opposite to the total change in potential energy. This means the sum of these energies always remains at zero. For both the x and y directions, the observed motion follows roughly the same pattern as the predicted motion. At later time values, the x position of the observed data begins to deviate more from the predicted model. This may be because the oscillation period was calculated using data from the y direction, which may not accurately capture the oscillation in the x direction. The motion between the observed and predicted in the y direction lines up pretty well, but the predicted data overpredicts the maximums and underpredicts the minimums. This can be accounted for by the fact that the system was not actually a closed system, and there were other things like air resistance and drag acting on the mass that were not accounted for in the predicted model. Is the energy principle satisfied in my model system? The easy answer is yes. To satisfy the energy principle, the change in energy must be equal to the work done by the surroundings. Since there is nothing acting on the closed model system, the change in energy must equal zero. In the graph, delta E, the change in total energy of the system, remains constant at zero. This is because the kinetic energy is equal but opposite in sign to the total potential energy of the system. Here's a comparison of oscillation periods between the x direction and y direction. For both directions, I calculated the oscillation period in the same way. I found the amount of time it takes to complete 3 total oscillations, and I divided by 3 to get the total oscillation period. As you can see, the oscillation periods differ between the x and y components. This means that you will end up with a different spring constant depending on which oscillation period you use. This difference will lead to lots of deviations, since the spring constant alters the spring force calculated, and this will have a domino effect on the other values calculated, like net force, velocity, position, and kinetic energy. Thank you for listening.